Welcome to this demo, to MLOps World Demo Days. I'm Jim Dowling, I'm CEO of Logical Clocks, and I'm joined by my colleagues Javier de la Rua Martinez and David Zavalva. And we're going to present the HopsWorks platform. And our name of our company is Logical Clocks, just to confuse you. So HopsWorks is an open and modular feature store. I'm going to talk also about its data science capabilities later, but I'm going to start with the feature store capabilities, which is why many people are potentially here. So HopsWorks is an open feature store. That means that not just that it's open source, but also it's open to be integrated with any data engineering, any data science, any model serving, and any compliance and regulatory framework. So the teams that are going to use the feature store, and typically we have data engineers, people who are responsible for the data from an analytics background potentially, the data scientists who train the models, the ML engineers who serve the models and put the models in production, and the architects who design the compliance and regulatory policies for the use of the data in the feature store. All those teams can use the tools of their choice in our platform. So if we start at the data engineers on the bottom left, our feature store, in fact, has a data frame API, so you can ingest data in Python pandas, so you can write pandas programs to compute features and ingest those features as data frames. You can also write feature engineering code in Spark or Spark SQL, and that can be in either Scala, Java, or in PySpark. And you can ingest Spark data frames into the feature store. So data can come in this way. And you can, of course, use Airflow, which is any Python client or any Spark environment. Now, you can also we also support external tables. That means existing tables with features, because many of you will have invested into existing infrastructure for feature engineering in Snowflake or SQL Server or MongoDB, and you'd like to leverage those investments. So I'll show you later on how we can take an existing table in Snowflake and just mount it into the HopsWorks feature store, and then we can use it just like any other features that are cached in the feature store. After you've ingested your data into the feature store and built pipelines to keep those features fresh and up to date, you use those features to train models. And you can do that from any data science framework. Typically, it's a Python environment, or it could be a PySpark environment, but frameworks like TensorFlow, PyTorch, Scikit-learn, XGBoost are very popular here. And then when you want to serve your features, so you've got some model serving infrastructure. It could be KF serving, Kubeflow model serving, Seldon Core, or it could be one of the managed cloud platforms like SageMaker. But then you can use our feature store to retrieve feature vectors at very low latency. And then finally, this is data for AI under management, so you need to ensure that your data is compliant and you're following all the regulations of your geographic area. Well, we are working currently to integrate with compliance and regulatory frameworks like Informatica, Calibra, Elation. So let's move on. It's an open modular feature store. So let's have a look at how we get data into the feature store. And I mentioned already that you could have existing tables in Delta Lake or Snowflake, and you'd like to add them to the feature store. So we can add them as external tables here. We call them on-demand feature groups. In fact, the tables in the feature store we call feature groups, but we'll get to that in a little bit. So that's one way of getting features in, just taking your existing tables and your existing databases and just mounting them as on-demand feature groups. And the other way that I mentioned is that you can cache the feature data in the feature store. And these are the other feature groups that we can see listed here. So one way of doing that is to have programs, and the programs can be written in any Spark or Python framework, as I mentioned. So it could be a pandas framework, pandas program that takes user profile updates from your data warehouse. And maybe this takes every update every day and runs once a day to update this feature group with the user information in there, user profile information. And you might also have a Spark program that runs once a day from your data lake to bring in web logs, process them, and push them as this logs feature group. But you might also have requirements for very low latency feature engineering. So maybe you have data that's arriving at your Kafka topic, and you need that data to be available to your model serving infrastructure within 10 seconds. And that's also possible. You can have a Spark streaming job that reads from your Kafka topic, does your feature engineering and writes to what we call our online feature store. So it's a feature store that it's the API to the feature store where we provide low latency access to the feature values. And the other classic user of the feature store, apart from these online clients, are the offline clients. So this is the data scientists who want to create training data, and also batch applications that want to retrieve large volumes of features to make predictions with them. Okay, we're going to do about 10 more minutes of slides, just that you're aware of that, before we kick off the demo. So that's getting data into the feature store. So what abstractions do we provide? So the first one I showed you there was the data frame API. So we actually introduced the data frame API. HopsWorks Feature Store was the first open source feature store to be released, and how it differed from the likes of Michelangelo and Airbnb's feature store that preceded it was that they used domain-specific languages for feature engineering, whereas we said, no, we'll support general-purpose programming languages like Python and Spark. So in this case, this model leads into the abstractions that we provide. So the data frames that we ingest contain sets of features. So the features are grouped together, and typically they come from the same source, and we update them at the same cadence. So these transactions, we can see here, transaction type and transaction amount, end up in a table called transactions feature group. And then we have this user features, which belong in the user feature group. And we can see the user ID is a primary key here as well. So this is where the features reside in the feature store. Another abstraction that we've introduced into the feature store space is this notion of training data sets. So what a training data set is a materialization of these features. So we're going to select a number of features in the feature store, join them together, that means reuse the features, and then store this training data on disk somewhere. So it might be in a bucket in S3, and it's going to be in some file format that we think we're going to need, because maybe we're going to train the model in TensorFlow, so I'd like to have my data in TF record file format, or CSV, or NumPy, or whatever you want. So what's interesting about the trained data set is that trained data set is a mapping, it's really a representation of your model, because typically there's going to be a one-to-one relationship between the model and the training data set. You'll have one training data set, one model, and that model will be trained with the training data set. And that means that the statistics that our feature store can compute over the training data set, things like the mean of the feature values, standard deviation, and so on, those values, that's metadata in the feature store, can be used for things like drift detection when you're monitoring your model in production. The model knows it was trained on this training data set. We can read from the feature store with a Python API or with a Scala or Java API, we can read up the mean and standard deviation values of the features, the min and max values, and we can do things like identify outliers and identify whether drift is happening on a particular model for a given feature. And Javier will talk a little bit about that towards the end of this demo. So if we go then from these models that we're running in production, it's a very abstract concept. What's the model serving servers that we support? Well, in HopsWorks itself, you can connect it to a Kubernetes cluster, and in the managed version, it connects to EKS on AWS and AKS on Azure, and you can run Kubeflow model serving servers from HopsWorks. You can manage them, and what that allows you to do is Kubeflow model serving in particular is that you can easily integrate the online feature store, the HopsWorks feature store, from this model serving framework. You have your AI-enabled application at the top, and it's going to make predictions, and it might pass in the user ID and maybe a transaction ID for a given. If we're looking at fraud prediction for financial transactions that we talked about. So in fact, maybe what we'll have is a money transfer between two users. A certain amount of money is transferred, but the model we trained to predict whether fraud happened or not, it requires a lot of context and history. It needs to know the user's interactions with this money payment system. Maybe how many times have they transferred money in the last day, week, month? Is there much fraud ongoing in the system at the moment? Does this user have an account with the bank, and has it been a loyal customer for a long period of time? All of this historical and contextual information can be stored in the feature store, and the way we get it is that we have our enterprise data up here, and we're going to have these feature pipelines that we saw earlier, the Python and Spark programs, that continually refresh the features in the feature store. They're going to keep updating the values. Every time we get these financial transactions, we're going to update the number of transactions for each user over the different time windows. We're going to update their credit scores as they change and so on. So this feature store will have this vast brain, as we can think of it, of memory of all of the interaction of this customer with this particular financial institution and with this particular financial product. So when a user wants to predict whether a given financial transaction is fraud or not, they'll pass over maybe the user identities, the amount of money sent, the banks involved, and then in something in KF serving called a transformer, we can go to the feature store to retrieve all of the features we use to train the model, and then we can then pass the full feature vector to the model. This is our model down here, and the model will make a prediction. Now, Javier will do in a demo later, we'll have a look at how we can collect the logs, those prediction logs to Kafka, and how we can then also even mine the data, the prediction logs, to do things like identify drift, outliers, errors, and even potentially create new training data. So I mentioned that HopsWorks is not just a feature store. So that's kind of the key feature store capabilities, and you can see there's quite a lot of infrastructure behind it. You don't need to add very much to make a complete open source data science platform, and HopsWorks has a complete open source data science platform. If we look at the left, we have the sources of our data here, and on the right, we have some output. So we have applications that are using these online models to make predictions, but you can have any other number of outputs. And the data coming in is typically coming from enterprise data, so data warehouses, data lakes, and so on. But there are, of course, third-party APIs, and a lot of data now resides behind REST APIs. So the typical way you would use HopsWorks for entire end-to-end machine learning support is that the platform supports Python, Spark, Spark SQL, of course, Spark Streaming, Flink, and you can do feature engineering in any of these compute frameworks. And we'll see that it's available as a managed service as well in the cloud, so a cloud-native platform on AWS and Azure today. And you can also install it on-premise or in any cluster, so GCP or any on-premise or private cloud. We have the feature store that I've introduced already, and then we also have support for model training, including support for GPUs. You can train with any Python library, and there is support for developing applications. So we have support for, obviously, source code control with GitHub and GitLab, notebooks, Jupyter, Jupyter Lab, and there's even a plugin for PyCharm and the Java equivalent, which I've forgotten the name for now. Yeah, okay. So once we've developed models and trained them, there's a model repository in the platform. And then you can also serve models using KF serving that I mentioned already. Now, underpinning the whole framework, we do have some unique technology. We have a file system called HopsFS, which has a HDFS API, but the underlying data, if you're on the cloud native version, will be stored in blob storage or in Azure and on S3 object store on AWS. So that's going to, we're decoupling storage from compute in our framework, and we're also keeping the storage costs low. And then finally, underpinning the whole platform, we have the world's fastest key value store with SQL capabilities called RonDB, and that we develop. And RonDB is quite unique because it acts as both the online feature store and the meta store for the whole data science platform. Right, Javier is going to do a demo later on. I'm just going to introduce the demo, and then I'm going to go straight into my demo. His demo will be about model serving and model monitoring in this fraud example. If you're curious, the code is, you can see a hyperlink down here to the code, and then there's also another end-to-end example for anti-money laundering in the bottom right of the slide, AML end-to-end. But basically what's happening here is that we have these financial transactions coming into our AI-enabled application, and it's going to ask the serving framework for the features that were used to, it's going to basically pull these features back that were used to train the model. So the online feature store will give us the features. Then the model itself will make the prediction of fraud or not and give a result to the AI-enabled platform. But we're not done there because these prediction logs will have a lot of valuable information. So we feed them to Kafka. From there, we can have a Spark application or a Spark streaming app for if you want to do 24/7 monitoring of your models, and Spark streaming is one way of doing it. And the Spark Streaming app will process these prediction logs, but also use the statistics from the feature store that we got from the training data for the model that we can compare with the live traffic coming from the prediction logs to see if drift is happening. And there's other things apart from drift, you have outliers, and ultimately you'd like to store some of those predictions back to the feature store so you can generate new training data potentially to have even better models and get what we call the AI flywheel going. I mentioned that the platform is available as a managed platform. It's also available as a self-managed version you can install on any platform. The enterprise version is slightly different. There is support for Kubernetes integration, GitHub, and single sign-on. But the open source version, everything that I'm going to show today, we're going to show, apart from Kubernetes integration, is available in the open source version. And you can go to the GitHub repo, and you can work with it and have a look at it. But HopsWorks AI is probably the best place to start, because that's how you can find out how to install things. So without further ado, I'm going to just go to HopsWorks AI. That's this link here. If you want to register an account, feel free to do so. There's no credit card required, no information beyond your name and your email, which you can make up if you want. Once you've registered an account, you'll get a demo cluster that you can try out. So the demo cluster is not super interesting in the sense that you're kind of in a sandbox. You can just kick the tires on the platform. What you really want to do if you want to get started is you want to connect your cloud account, so your AWS account or your Azure account. And once you've connected your AWS account or Azure account, we will give you $4,000 of free credits. You'll need to create a cross-account role on AWS, and on Azure you create a subscription ID and tenant ID. But then you can go off, and you do have to pay for the virtual machines that will be created. So you can go ahead and create clusters. I'm not going to create one now, but just to give you an idea of the kind of things you need to do, you need to have a resource group already and a storage account in Azure. Similarly, an S3 bucket in AWS. You can potentially connect to Kubernetes if you want. You'll need a managed identity. And then if you want to set up like a RonDB cluster, the separate cluster, you can do that as well. I'm just going to go into a cluster that I created. I'm going to look at this one. I have a few of them here, actually. I have one with Kubernetes, and this one it's called Snowflake. And I have another one down here. So when you create this cluster, you can see there's a link to it here. And you can, of course, set up single sign-on. I haven't done that for this cluster, so it's going to have a username and password to get me in. But if we click on details, we can see here that the cluster is an elastic cluster. You can add and remove workers. So I can add workers, use spot instances if I want. If you're going to use GPUs, you can select GPU machines. So it's really nice. You can mix and match. You can actually add a GPU server, a GPU server to an existing cluster. You don't have to have just dedicated GPU servers or just dedicated CPU. You can have mix and match of those virtual machines in the same cluster. And we have also the ability to set up auto scale. So if you want, for example, to do feature engineering jobs at 4 in the morning, and you only want to pay for compute at that point in time, well, then I would advise you to configure autoscale. And when you configure autoscale and submit a job to the platform, it will allocate the virtual machines, run your jobs, and then deallocate the virtual machines when the jobs are complete. So that's basically how you can control your cluster. There is support for backups. You do have to stop a cluster to create a backup. It's an incremental backup, not a full backup. So that means it's fast. I have to click on these open ports. I'm going to do a demo where I use the feature store from Colab. And Colab is outside of AWS, as you probably know. So that means I need to open these ports. Not all of them. I don't need SSH to be open, but leave it for the moment. And that way Colab will be able to connect to the cluster. Otherwise, of course, it will be running inside its VPC, and the only port available will be 443, which is this one. So this is HopsWorks when you log in. This is what you see. And you can see that there's this try out the new HopsWorks. And what I'm going to do in terms of the demo is I'm going to do the feature store first. And I'm going to do the feature store for people who have an existing data science platform or do feature engineering on Databricks or any Python environment. And then after that, we'll go and look at the wider data science platform. So I'm going to click on this one that says try out the new HopsWorks. So this is the new HopsWorks UI. It's a feature store dedicated. It's it's complete in terms of feature store, but there are some parts missing in the wider data science platform. So what we can see here to begin with is that we have these things here called projects. And the projects, you can create new projects. A project is a sandbox inside the cluster. So the cluster is a shared resource, but we have security inside it. We call this multi-tenancy, project-based multi-tenancy. So inside each project, we're going to have some users, and there's going to be obviously data. So there's a feature store for each one of these. And you can even have programs and so on. Now, so one use case for this, of course, is that you can have a production feature store, you can have a development feature store, a staging feature store, and you can even give each developer their own feature store if you want. Another use case is if you have sensitive features. So often you would say, well, I'm going to create a whole new cluster for my sensitive features. And ordinarily, that would be a wise thing to do, but you can also do it here if you so choose. In HopsWorks, we guarantee this sensitivity, that sensitive data on the shared cluster can be, we can guarantee that only the people who are members of this project and only the people who have the appropriate role within that project will be able to access the data. I mentioned the term role. I'm going to go into this demo feature store here. And when you create a cluster, you'll get this new demo. And if you click the demo button, it will create exactly this project that you see here and the feature groups that are in here. So I mentioned that you can have multiple users in this project. You can see here we have the members here. And there are 2 members. And we can see there's a role here as well called data scientist. And then there's another one called author. So in fact, the 2 roles, so I was the author, and the author is also the what we call a data owner. And you can't change that role, but other members of the project, I'm the owner of this project and the author of it, so I can change the actual role of these other users. So I can say this person should be a data owner or data scientist. I can add new members, and I can say Ricardo should be a data owner, which is in line with GDPR's notion of data owner, that you're responsible for the data inside this. So this is really an example of self-service and even data mesh, if you'd like to call it like that. Now, which is a buzzword that I don't tend to go into. Okay, so we can see the project overview at the top, that this demo project has 8 feature groups and 1 training data set. And I explained what feature groups were and training data sets already. You can integrate it with Databricks. If you want to do your feature engineering in Databricks, well, what you can do is, if you click on this button, you can add a Databricks instance, and I had one open earlier. I'll go back here. Oops, too many windows open here. So this is my Databricks cluster that was open earlier. Am I still logged in? I am. How do we get back to the main page? Yeah, from here, what I can do in Databricks is I can click on user settings, create a new token, and then with that token, and then this is the cluster ID at the top here, those 2 pieces of information. So the instance name is the URL, and then the API key was the one that I created there. What I'll get back is this here. You can see here that these are my clusters, and I have 1 running. And basically, if I press this configure button here, what it will do is install the libraries that we need in that Databricks cluster to read and write from the feature store here. Now, if you're not using Databricks, if you have a different Spark cluster, what you need to do is basically download some jar files, download a certificate, so it's a key store and a trust store, and then configure your Spark client, so the Spark conf file. And you add these settings in there, and then your Spark application running in EMR, or running on Cloudera, or running on HD Insight, or Dataproc, it'll be able to read and write to the feature store directly. So we don't have this notion of ingesting features in the HopsWorks feature store. If you're using a Spark client, it's writing directly. It's not going to write the data to disk first and then run a separate job to ingest the data. Effectively what that's doing is doubling the amount of writing we're doing. In this case, it can write directly. Now, the other type of client that we have here, it says connect to the feature store. This is the Python client. And I'll do an example of this later. The Python client can basically install this library called HSFS and then connect with an API key. And your API key can be stored in a secrets manager. That's the most secure place for it, or in a file, which is okay if the file has correct permissions. And you can also just paste it into the your notebook if you really want to, and that's what I'll do because it's easy to get started with, but it's not a secure way of doing it. So in this case, we need to, when we're outside HopSearch and we want to connect to it, we need to put in the DNS of our feature store instance, and then the port, which by default will be 443, and that you shouldn't change that. And then we have the project name. So this project name is this one here, demo_fs_med10180. Okay, so that's the basic overview of this feature store. We can see there's 3 parts here: the storage connectors, training data sets, and feature groups. So I'm going to start with Snowflake. I'm going to start with rather than writing a program that will ingest data into the feature store, I'm going to start with an existing table that I have in Snowflake. So this is my Snowflake cluster over here. And we have these things called databases, and we have worksheets. And this one is called, the database is called ML_workshop, and we have a table called customer churn. So I clicked on preview data, and we can see here there's a bunch of data inside this table. And we have customer ID, state, account ID. It's a table that's related to whether a customer has churned. We can see that there's a label in here. Did this customer churn, yes or no? And we can see false, true, false. And there's quite a bit of data in here. I'm not going to go through all of it. It's not that much. It's 3,333 rows. But what I'd like to do is I'd like to make this table available in the feature store. I'm not going to copy the data over. I'm going to use it as an external table. So what I need to do, and if I go back to HopSearch here, is that I need to go to my storage connectors. And I need to set up a storage connector to Snowflake. So here you can see we have a bunch of storage connectors, S3, JDBC, which covers most databases, relational databases, and even non-relational databases of JDBC APIs. This is our file system, HopsFS, and then you have Redshift, which is a popular data warehouse on AWS. Azure Data Lake, and both Azure Data Lake and S3, if you have data in Delta Lake, so in Databricks Delta Lake, then you would choose either Azure Delta Lake or AWS S3 as the protocol, and then put the path to the object store for Delta Lake in here, and that's how you can connect to Delta Lake. And then finally, the Snowflake is an example I'm going to cover here. The connection URL would be the one at the top here. We can see it's this one here. Again, it's the domain name of my Snowflake cluster. Oops, we'll close that. Am I on the correct one? Yeah, sorry, I have too many of these open. Let me just close them. Let's reconnect. I need to, okay. It's warning me. Okay, so here we're on Snowflake. So we're going to put in that name there, the username, password or token, database schema. Of course, I've set this one up already. This one here, this SF connector. And basically then I've already created this as an external feature group. And you can see this is what it looks like here. Now I'm up in feature groups. So that Snowflake table is available inside the feature store as a feature group. And we have other feature groups in here that are not external tables. This one is an external table because it's called on-demand. So on-demand feature groups are external tables in our platform. And this one here is cached. So I'm going to put a C for cached. And we have a bunch of these feature groups here. So I'm just going to show you all of them. They all look the same. So players features, attends features. This one is green because it's available both online and offline. And then this one's called Hoodie and Games features. So Hoodie, you can see here that when we create feature groups that are stored on our platform, by default, they're actually Hoodie tables in the offline feature store. And Hoodie is effectively Parquet data, so it's Parquet files with some metadata on top of it. So Hoodie is very similar to Delta Lake by Databricks, and both of them provide ACID properties on top of Parquet. So when you do updates to these tables, when you add rows, remove rows, delete rows, any updates will happen atomically, and you'll be able to make incremental changes to those tables. You won't have to drop them and recompute them. We can see here, if we look at this particular Hoodie table, we can see what has happened over time, activity. There were some rows added and none deleted and so on. And here's the job that was used to compute these features. And here's the version of the schema, because we have support for schema versions here as well. So you can see two types of versioning here. We've got the schema version. So if we make breaking changes to the schema, we can have different versions of the schema. And then every time we make a change to this feature group, we read or write, we'll get a new commit ID that we can inspect over time. I'm going to start to go back to the Snowflake one. The point here was just to show you that all of these features, irrespective of whether they're stored on our feature store platform or in external systems, look pretty much the same. So if we go into the Telco Snowflake feature group, we can see here there's 22 features. It came via this storage connector. How do we create it? Well, it's a very simple command where you can basically say in a notebook, and we can show you examples here. You can see here we have a bunch of example notebooks, and you can find it here. So I'm not going to go through that one for the moment. I'll go through how to create feature groups in a minute, but we'll just look at the user interface for the moment. So here we can see there's the 22 features that we have in Snowflake, and that's these ones here, and we can see the types of them. And we have this area called provenance. So if these features are used in any training data sets, we'll be able to know if these features are being used. So it says this feature group is not used in any training data set. We also have something here called expectations. So we can add expectations to feature groups. And expectation in this case, you can see it says completeness. Completeness is basically means there's no missing values, no nulls. And in this case, we can say that for this feature, international minutes, we have completeness value of 1, which means no missing values. And then we have support for schematized tags. I'll get to that later. This is for governance. We're able to define our own sets of tags grouped together and including types for those tags. So that means as an architect, you're able to define how these features should be used and how they are used. Like, for example, what you might have a tag is saying, this data is personally identifiable information, and this data comes from the EU. And that might have implications for whether you can use these features in this feature group when you're training a model or not. And the other classic ones would be retention time for features. You can basically design your own governance rules with schematized tags. It's a very flexible mechanism. We can see on the left, there's no data preview available. So for these on-demand feature groups, we don't support previewing the data, but we can look at the statistics. So when we mount this feature group in, we can see there's descriptive statistics for the account length. We have min, max, mean, standard deviation, and some distinctness, completeness, uniqueness, distinctness, and entropy values for this particular feature account length. And there's 22 of these features, and you can go through all of them here. And then we can see the activity when this feature group was created. And we can see the person who did this. Now, so if we go back and look at this, again, we can just compare it to what we had here in Snowflake. That wasn't this one, it was this tab here. Yeah, we can see here, all these features here. And one thing to note is that we did lowercase them. So the platform does actually lowercase these features when it ingests them. That's just something that might be worth knowing. And when we create a training data set using features, and I'll just show you how we do that, because these are the training data sets. They're very similar to the feature groups, and I can do it from the user interface, and we can also do it from a program that will do that later. So I'll just call this like Snowflake, whatever, hello, just call it Snowflake, and then you can give it a description, pick a source where you're going to save the training data. I'll just save it to our file system. Pick a file format, I might pick TF record, and whether you want to compute statistics over it or not. If you want to have some tags, I have one called privacy there. I'll skip that for the moment. Keywords, which is not a tag, it's just an individual keyword. I might say this is PII, for example. And then we can pick the features. So we want to join features together. So maybe I'll pick one from here. I'll pick a couple from here. And then we can go back. Now, the only thing about this is you do have to have a join key, which is very interesting, because I know I'm picking features where I don't have a join key between the different feature groups, because this feature group here is about players, and the other one is about telecom customers. So what we'll see when we come down here is that there's no, the system can see there's no join keys available between them. So I would have to remove these and then pick other features. Say, okay, we'll remove that one. And then we can pick some other features from a different feature group. Let's see if we have something here. Oops, add some features here. We go back. And then we can go ahead and create the feature groups here if we want to. So it finds the common join key here, which is team ID, and we can configure splits, like training is 80% training, and then tests, maybe 20% test data, and you can have validation data sets as well. And then you can create a training data set, and this will kick off a job to create that training data set. Now, I have a training data set that I created already, which was this one, the tour training data set. And if we have a look at it, it looks pretty much like the feature groups. We can just see the data. The only difference here is that the data is stored on disk, because when you train models as a data scientist, you typically will train with file data. So you're going to have TF records, CSV, NPY files. And we can see where these features came from, which feature groups they came from. And it looks pretty similar. Okay, let's have a look at some code. So this is the basic overview. There are some other things I haven't shown, but we'll go into them. Let's just cancel the feature training. I'll start with looking at these schematized tags. So I can create a new schematized tag here. We'll call this one MLOps world. And we can add properties here. So we can have one like govern. And govern should be Boolean, is it true or not? And we have to, that's a required field. And then we'll call it, maybe location, country. And maybe you have to put that in where you're from. So you can basically define these schematized tags, and then you can attach them to any feature group or training data set in the platform. So we can go into this feature group here called Teams Features. And we didn't look at some of the statistics for it, so I'll just go through some of the statistics. We can see here the correlation matrix I didn't show, so we can see that there. And the data preview I didn't show, because the data preview is only available for these cached feature groups. So we can see quickly get a preview of the data, and that's very useful. And the other thing I forgot to show, and I'll do it now, is that we can look at activity. So if we look at this particular feature group here, and we look at activity, we can see all of the events that are happening to it. So we can see a validation event occurred. We ingested some data, we ran the job to create the feature group, and so on. There's quite a bit of information there. Now, what I was going to do there was I was going to just attach we can add keywords. There was one called PII. I can add the PII one here. And the keyword is visible in the UI. They're quite easy, but there's no value associated with it. So if we want to have tags with values, then we need to use these tags here. And I can have the MLOps world 1. And maybe I'm going to write Ireland in here, and govern is true. And I'm going to save this feature group. And then these tags, it's useful to have them, but how can you find them? Well, we can actually free text search for them. So I can free text search here for Ireland, which is not fully Ireland, but you can see it hits it on the tag. So it's, behind the scenes, it's using Elasticsearch to index these. We can look for PII, and we can see the keyword that we attach to it. Now, you not just search for feature groups, you can search for trained data sets, you can search for individual features, which is quite useful. So if I search for individual features, you can see I can find this feature here, it's team budget, and I can quickly look at the distribution of values, or maybe team position, and we get some statistics for them. And you can get quick previews of individual features as well. Now, here's another MLOps feature that's very useful, is that when you're developing new features, you might have your own feature store, you might have your own development feature store. And I want to see if anybody else is developing a feature currently across all the projects with the word like Ireland or something like that. And you can see it's only finding this feature group here. And if I make it a bit wrong, at the end, there's nothing in there. Okay. So that's pretty much it for the governance, and this is what the feature store looks like. So let's look at how we add data. We use programs to compute features and write them to the feature store. And how do we create training data sets? How do we use the online features? And Javier will have an example later, a full end-to-end example with monitoring and using the online feature store. I'm just going to go through the very basics of feature engineering. Now, what I would recommend you to go to is this website, examples.hopsearch.ai. It's part of the docs.hopsearch.ai site, so there's quite a lot of quite good documentation here, I think. And this tells you about the abstractions and the API and how to use it and so on. But if you just want to see example programs, you can see this not Hopsworks AI, but the examples link here gives you a bunch of notebooks, right? So, and these notebooks are mostly in Python or PySpark, and there are some in Scala, because there is both a Scala Java API to the feature store as well as the Python and PySpark API. And I'll just show you the quickest way to get started. If you have a Google account, you can click on the Colab example here. Now, to run this example, you will have to have a cluster. So you will have to connect your cloud account and start a cluster running. And what you need to do is run the cell. So firstly, it's just going to install this library, HSFS. And then what you'll have to do is you'll have to enter in the UUID to the Hopsworks cluster, the project name, and then the API key value. Okay, so I'll just show you how I get those. We'll go back here. So I can create an API key from my account settings here. And, you know, it's MLOps world. And you can give it a bunch of permissions. So you can go create, and then you can copy it. I actually have one already, so I'm not going to put that one in here. So let's go back here. And this is one that I'd run earlier. I'm going to rerun it so we can see it. So it's connected to a virtual machine, or I'm not sure if it's a container, what it's connected to in Colab. I guess it's a container. It says a Python 3 Google Compute backend with not quite a gigabyte of RAM and some disk. So it's basically going to install our library first. It says it's the following packages. You must restart the runtime. So I guess I'll restart my runtime. It's telling me to do that. And while it's restarting, we can see here that I've already put in, this is the host name for the platform. This is the project name, and then the API key value is here. And I created that one already. I'm not too worried. This is a throwaway cluster. So this is the platform here. And this is our cluster. This is the UUID, which is up here, and the API key I had earlier. And then the project name is this one here, DemoFS 10180. So we can see it that hopefully should be correct. DemoFS 10180, yes. So I hope the restarting worked. I'll just try and connect and we'll see what happens. So this HSFS library, it works in both Python and in PySpark environments. So I'm just going to run through the cells here. So the first one is that I'm using the engine Hive, because by default the engine is Spark. But if you're going to use Python client, you change the engine to Hive. So you can see I issued this query here to say, hey, I'm interested in the feature groups, or the Teams features feature group version 1, and just show me some values. And if I don't put in the version number, it'll give me a warning and tell me you should put in your version number. It defaults to version number 1. And it's good practice to have version numbers for your schemas, because if you want to write code that will continue to work when people upgrade or update these feature groups, and they're either going to drop columns, add columns, and go to the next version of the feature group, you want your code to continue working. Now, I'm going to just go through some example notebooks here. I'm going to ingest some features into the feature store as a feature group. And this is a Python client. So what's going to happen is, firstly, I'm going to try and get this feature group. And if it doesn't exist, the exception will be thrown, and it's going to then create the feature group. So you can see here it says it actually created the feature group. So this feature group didn't exist. The feature group is called name country. And we can see there's a data frame called df. Now, where is df? df is here. Okay, so df is actually just reading some data from this URL. And this URL is I have some data clean trained. It's called the CSV file. And it's downloaded that into the data frame object. And what it's doing is the Python client is actually copying this pandas data frame to the platform. And then in this case, for Python clients, we don't write directly to the platform. We do run an ingestion job. So if I click on this link here, it'll bring me to the platform. And you can see this UI looks different because this is the full data science UI. And you can see it started running this job here. There's a feature store button here. There's Jupyter, there's experiments, models, data sets, and so on. But it started this job running. Now, if I look at the job, this is the name of the job. So it created this job and it started running. I can click on this. I can stop the job, or I can get info about it. And I'm going to click on the monitoring UI. It's a Spark job that it started running on our platform. So you can see the cluster utilization went up because this cluster only has, it's very small. It's just one virtual machine executor, and then we can look at the Spark job itself. It's going to apply any data validation rules we have. Actually, there's 2 executors on that are currently running, and you can get your logs and do all that kind of stuff. We also support in the UI Grafana to look at the performance indicators for your job, so you can inspect its performance, and you can also get live logs if you want to, without going through the Spark UI. We also store the logs to Kibana here. And this is actually really useful if you're running a Spark streaming job, because then you can, you can search your logs here, and you can do lots of things with Kibana with logs. You can even do charts and so on. And there's a Yarn button. This is running our own version of Yarn as a resource manager we're running in our cloud native platform. So what I'll do is then I'll actually just show you, this is the new UI, and you can see it, this is the old UI, the data science platform. It's the same as before. We have projects here, and then we have these tours to get you started. And I'm going to go into the project that we're looking at called Demo FS. So let's go back to our Colab notebook and see what's going on here. It's that job, you can see that it returns in the cell, so we don't know if the job's completed. So what I can do is I can just look here. We can also do it from the UI, but I'm pretty sure the job is finished and it's succeeded. We can get the logs for the job, error log here. I don't think there should be too much. We can get the output logs. It says it's too big to display, so I can download it and then look at it from here. So I can just look at it as if I want, I can just search it here. It's printing a lot of stuff. And yeah, you can then get the info for the job, where it was, and so on. Okay, so and for jobs we have in the platform we support for Flink, Spark, Python, and actually any Docker container if you connect it to a Kubernetes cluster. So actually this one's not connected to Kubernetes cluster, so when I want to create a job, it only gives me Spark and Flink, because Python jobs are also run in the Kubernetes cluster. But that's okay, and that's what you'll get in the open source version as well. So let's go back and look at our notebook. And where were we? We're going to go here. We have this just to print out the feature group description. So I'm going to I haven't talked about this, but I'm going to we're going to ignore this one actually, because that one is, what we're going to do is this expectation rule is not defined. Okay, let me see. So we can see the expectation. Let's have a look at this one. Let's skip over that one. That's an expectation. I haven't talked through the data validation rules here, but we'll skip over them for the moment. And I'm going to run another job here. So this one is going to actually update the data in the feature group. It's going to actually, the data in fact there is just first name, last name, and country. So it's going to add some new rows, and then we can follow its progress in there. So, and then there's a bunch more rows. You can see all this, and you can go ahead and run these yourself. So let's go back and look in the feature store and see what's happened. So when we ran this feature engineering job, you can see this is the feature group that got created. It's called name country feature group. The job is probably running because it's trying to, yeah, this is the job that's running in the ingest data. We're ingesting one at the moment, but we can still go ahead and browse it. We just name country and last name. It's a hoodie feature group, so the data will be stored in the file system in hoodie. We don't have any expectations attached at the moment. And if we go back to look at the activity, we can see that the feature group was created, we computed some new rows, and we ingested some data. So that's basically how you would create what we call a cache feature group. The data is available both in the online and offline. And if we look at the data preview, in this section, you can preview the data from both the offline feature store, which is querying Hive, and in the online case, it's going to query RonDB, which you can see is a little bit faster. Okay, let's go back to the job is still running. Let's go back to this platform. So this is HopsWorks as a data science platform. Now, what we can see here is we have our project. So I'm going to actually go into this project that we had here. I'm actually got logged out here. Okay. So if we go into this project here, we can see that there's a number of services on the left-hand side. So we've got members of the project, we've got Python libraries. So each of these projects has a set of Python libraries. In fact, there's a base Docker image for each of these projects. And then we get a Conda environment that's on top of the base Docker image. So data scientists who want to use new Python libraries can just search for them. You can just say, okay, Panda, I want to have some form of Panda library, and then I can click install, and it will install that library, and it will be added to my environment. And what actually happens in the background is that we compile a new Docker image, which is the base Docker image plus the current set of Python libraries in your Conda environment here. You have to you can follow it here in ongoing operations. And you can use Conda channels as well. You can change the Conda channel, Conda Forge. You can upload requirements files, YAML files, or Conda YAML files, wheels, eggs, and even stuff from Git. So the first time you run it, it's going to clone your Conda environment, so that you have to wait a couple of seconds for that. If we want to run, let's say, a Python notebook, we can check out code from GitHub if we want to, or GitLab, and you'll need to use an API key. So you need to actually add a secret with your API key token in here to do that. I'm going to just start, you've Jupyter Lab or Classic Jupyter. I'm just going to start Jupyter Lab. Actually, I'm not going to start it from in this project because I don't have any interest model training jobs in here. But what we can do is we can create a training data set from here. So I click on Jupyter Lab. It starts a Jupyter Lab instance. This is our notebook server. And when you've run this demo project that we've seen here, there are a lot of notebooks here. And I'm just going to show you the HSFS ones. There's a basics level here, and I'm going to look at the one called training data sets. So in this case, for training data sets, I'm going to start running this code here as well. It's a Spark application, so it's running as a Spark application in our cluster. And in fact, I can see it's not going to work just looking at it because I haven't created these feature groups. So I do have to run the feature engineering notebook in order for that one to run first. I'm just going to stop this one cell, and we'll discard the changes and then run the feature engineering one first. Okay, so I'm just going to run all of the cells. So in this case, this particular notebook, what it's going to do is it's going to run a Spark application, connect. You can see we don't need to pass in the credentials because it's running on our platform. It's going to read up 3 different CSV files and create 3 different feature groups using the CSV files, doing some feature engineering here as well. And it'll create a number of feature groups. So you can see this is the kind of feature engineering that you would typically do with aggregations. So the number of sales in the last month, last quarter, last 6 months, last year. And then it's going to create some feature groups. So we've got a sales feature group. We've got exogenous feature group. And then we have, yeah, it's the same example. So we can delete the feature group as well. We can show you that. So, and we can append features as well. We can get new versions of them. So when that starts running, I'm just going to go back to the platform. And you can see actually there's 2 apps running. So if we go back to Jupyter Lab, I might say, well, okay, let's shut down the training kernel. Okay, and you go back here. So that we just have this one application running here. So we can actually see the Spark UI as well to this application when it starts running. And we can get the logs and so on here. So for these jobs that's running as Spark jobs in the Spark UI, sorry, the notebooks running as Spark jobs in the platform, we can still use a Spark UI here to have a look at them and see how they're running. Okay, so you can see there's one executor running in there. So let's keep going and have a look at a few other things in the platform. I'm going to move, we have a data sets here. This is a file system. And you can see that we have like training data sets are really just folders. You can see this is a folder in here, and it has TF record files in here. You know, if you want to use these training data, you can just copy this path. We've got the HDFS path to it. We can just use it then in any TensorFlow or PyTorch program or scikit-learn program. Read it up into a pandas data frame or read it up into a data set in TensorFlow. But I'm going to go to another project because it has a bit more about machine learning in it. And this project is, you can see it's called Demo ML. And the way you can create it is basically by running this deep learning tour here. So this is Demo ML. And what I did earlier was I actually ran a notebook. So I ran a Jupyter notebook. I don't think it's still open here. We can open it up. So this notebook, have a quick look at it. See if it's open. So what you'll notice as well in the platform is that you can have many concurrent users. This is not a single user cluster. We can have as many concurrent users running as many Jupyter notebooks and so on in parallel on a single cluster. So I ran this notebook, and this notebook is just a classic Keras TensorFlow program to train MNIST, which many of you are familiar with. The only difference we did here was we defined a function, and then that was a function that got distributed to the container or worker to execute it. And if you have GPUs in your cluster, we can run that on a GPU. So I can shut that down because I'm not really doing anything with it. So what happened was it actually created this experiment here. So this experiment is the result of that notebook that I trained, and I didn't train it for particularly long, but we can get the log of the training, so that's why the accuracy is not that high. You know, the log is basically telling me there were no GPUs. We can see a model was output. We can see there's support for TensorBoard here, and I'm going to start the TensorBoard up as well. And we can see also that we have a program. We get a copy of the program, a copy of the notebook. That program was exactly at that point of time, a copy of the Anaconda environment in case it changed over time. And then we get the experiment directory. And then we have this TensorBoard for this run. So here we can see the TensorBoard and the training. It didn't go on for that long. It only went for 2 epochs. So, you know, it didn't perform that well. But TensorBoard is a really powerful platform. We have a bunch of plugins for GPU profiling, hyperparameter tuning, and so on. What we can also is look at the directory. So when we train the model, and because we have this distributed file system, you can train on many workers, many GPUs, and all of the files get collected here in this distributed file system, which is incredibly convenient. There's no notion of copying files from containers. If we go back to the experiment, we'll also see that a model was output, and this is the model registry here. We can see here that if I close it, I can search for individual models and they can have versions. You know, I have filters. So I've only got one model here called MNIST. You can have multiple instances of the same model with different versions. When we train the model, we return. So when we save the model, we can save a dict with the model, and I saved a dict with accuracy, but you may have your own user-defined variables, so you can have these tags in here to understand your model. You can click on this link to find out you know, the experiment used to train it. We can also, if we train it from a training data set in the feature store, we can go to that and navigate to that. In this case, I didn't. And that gives us kind of provenance capabilities. And then this model itself, if you want to use it in a batch application, you can basically navigate to the model. This is the model, and this is the protocol buffer file. So I can copy this HDFS path and run any program that wants to use this model, any batch application that wants to use the model can just read it up as a file. I can read it from an external Databricks cluster or Spark cluster as a HDFS file, for example. Now, once the models are here, we're able to also serve the models. So I started this model serving earlier, and model serving, you have TensorFlow or Flask currently. We also have Kubeflow model serving that Javier will show in a minute. And then we can pick our model, give it a name, give it a version, and then create serving. And if you're connected to Kubernetes, you can have many instances of it, and the logs are stored to Kafka. So any prediction logs, we're going to log to Kafka here. So this one is running already, you can see, and we can have a look at the logs as it's running. They're collected, and we're getting them from Kibana here. So this way you can see what's happening on your model. And then the last thing I'm going to show here is Airflow. So we do have support for Airflow in the platform as well. I'm not sure if I have any jobs in here. I do. So in Airflow, what we can do is, I'll just show you how to create a quick Airflow workflow. So we'll call it 2-step. And what you can do is, with this UI, you're able to create a very simple Airflow workflow. I can say number 1, and I'm going to wait for that job to finish. That's going to be the first job that I had here. And then I can say job number 2. And I'm going to wait to finish and run after job number 1. So it's a very linear, simple DAG. It's going to run job number 1, then job number 2, and I generate the Airflow DAG. So this 2-step, and typically training pipelines would only be creating your training data set, training the model, and then validating the model on different slices of the data. So this program itself, we can look at it here. It's a very simple Airflow DAG, a Python program. It has these 2 hops operators, the first job and the second job. So just to remind you, those jobs are these jobs we see here. This is job number 1, and it's a PySpark job. And then we have job number 2, which is another PySpark job. So if we go to Airflow, we can open Airflow here. And you can use your own external Airflow cluster if you want, and then you can turn on these workflows and have them run. Now, I've been talking for quite a while, and let's go back to I was running this notebook here. I do realize that, but I'm kind of running out of time. It created these feature groups, and then what I can do is I can run the second notebook here, the training one, train data sets. And this should, we can go run all cells. So this will create our training data. So that's the last thing I'm going to show before handing over to Javier. So I'm just going to shut down the feature engineering one. So it is a shared cluster. So I can shut down the first job to free up resources for the second job. So in this case, the training data set, this is the last thing I was going to show. We have a very nice API for creating training data sets. You get your feature groups, and you have this one called sales and another one called exogenous. And in this case, we're going to join the sales features with 3 features: fuel price, unemployment, and CPI from the exogenous feature group. So we get back a query object. Now you can get a pandas data frame from this and train models directly, or you can save it to materialize it to files. So you could put it in an S3 bucket. In this case, it's just storing it to a CSV file, and it's going to be in our file system. And then you can hear we're saving a different version and so on. And then you can see we can make it more complex by adding splits. And then we may have a connector to S3, for example, and store the data in S3. And you can see you can also create these training data sets directly from data frames. So there's a bunch more of these examples. Of course, I wanted time to go through all of them. I'll just point you back to this examples.hopsworks.ai page where you can see them. Now, with that, I'm going to hand over to Javier. I just wanted to actually show if that training data set got created at this point in time. Yeah, this is our sales model. So this is the training data that got created by running this Jupyter Lab notebook here. And we're also able to see that in the file system if you're curious, because remember, it's materialized in the file system, and that's it in here. So with that, I'm going to hand over to Javier, and I realize I've used up a good bunch of time. Javier?
Yeah, all right. I will start sharing the screen. All right, I hope you can see the screen here. So yeah, I will proceed with the end-to-end demo for card fraud detection. So we have here 7 notebooks. I will just run the last 2 because it takes some time, but you have these notebooks available in the repo GitHub following the link that Jim showed in the last slide. So starting with the first one, we are going to create 4 feature groups. So for that, the first one will store the financial transactions, and then the other 3 will store aggregations of the transactions activity at different rates. So we have 10 minutes, 1 hour, and 12 hours. And these aggregations consists of the number of transactions that and also the average of the amount of the transaction and the standard deviation. So first we can define the schema that these feature groups will have. Then we can create empty data frames following this schema, and we will use HSFS, which is the Python library to connect with the HopsWorks API to generate a connection that, as Jim mentioned before, we don't need to specify parameters for the connection if we found this in the platform. And then we can proceed with defining the metadata object for the feature groups. So in this metadata, there are a couple of things that we can specify. We can say specify if we want these features to be available online in the online feature store. Also, we can specify a version. So this is useful, for example, if the schema will change in the next data that is going to be ingested. We can just we have to define a different version here, and we can specify if we want to compute statistics on the feature values. So for now, we don't need to compute the statistics, but we will see that later for creating when we create the training data set. And then also we have to specify the primary key. So here in these 4 cells, we can define the metadata objects for the feature groups, and then when we call save, specifying the data frames, we create the feature groups. So in the second notebook, we will use Faker to generate some synthetic data, some fake credit card, financial transactions. And well, I don't need to go into much detail. You can have a look in the GitHub repository, but basically we create unique credit cards that look like this, and also we will generate different timestamps for the transactions, and also different amounts which follow a Pareto distribution, which is more common. Basically, smaller amounts of money are more common than the bigger ones. So we will follow this distribution to generate the transactions. And then we can combine these columns together, which are the transactions themselves. And then after that, we can just create chains and modify the transactions to simulate a fraud as well. So after that, we will, if you having in mind the estimating in which we have an AI-enabled platform that will continuously send logs of the credit card activities, so the transactions, to a Kafka topic. These transactions will be ingested in the online feature store, and these aggregations that I mentioned before are going to be continuously computing and ingesting these values into the online feature store. And then we will use this data to enrich the request when we want to make predictions about if based on the recent activity of the credit cards, if the credit card is fraud or not, it has been fraud or not. So for that, we will send all these transactions that we have generated to a Kafka topic, which is this one that we have here, credit card transactions, to simulate this continuously ingestion of credit card activity. So then in the next notebook, what we will do is to, using the same topic, we can use HSFS to read, to consume this Kafka topic and continuously ingest it into the online feature groups. So for that, we can create a streaming query in Spark that reads from this topic, and we have to specify the schema that the topic has. And then what we will do is to compute the different aggregations that I mentioned at the beginning in 10 minutes, in 1 hour, and 12 hours. So we will have 3 streaming queries here. And with these streaming queries, in order to ingest the feature values into the, in order to ingest this data into the online feature store, we can use HSFS to get the metadata objects of the feature groups, and then by calling insert stream, passing the streaming query, we can continuously ingest this data that it's been generated in these queries. We can see the state of these queries, if it's active, also the status, if it's waiting for data, or if it's already processing, or if it's done. In the meantime, we can also check if some values already arrived to the online feature store by running SQL queries. And then once we have data being ingested in the online feature groups, we can use Hoodie to send this data as well to the offline feature groups. So in this case, we have here the 4 the 4 cells where we will ingest the data from the online feature groups to the offline, and after that we will use this data from the offline feature groups to generate the training data set, and then we will train a model with that, as we will see later. So in the same way, we can check the status of the queries, but in this scenario, we wouldn't stop these queries, because we want to simulate that this AI-enabled platform is continuously sending more and more transactions to the topic. So given this scenario, we wouldn't stop these queries, but we can do that just for the demo. And then after we have already values in feature values in the online feature group, we can proceed with training, generating a training data set. So for that, we can use again HFS. What we will do here is to what we can do here is to create transformation functions. So in this case, for example, we are creating a transformation function to normalize the feature values. So we can create transformation functions at the feature store level. And what this allows us is to reuse this transformation function in the different points in your data pipelines. So for example, for this demo, the same transformation function will be used in 2 cases. When the training data set is generated, it will be, all the features will be normalized using this transformation function, and also when we serve the model, and the model will retrieve the serving vectors from the online feature store, we have to apply the same transformation function to these values in order to make the predictions, in order to avoid the training serving skew in the data and so on. So when we want to generate the training data set, we can get the feature group objects and then define a query. This query will join different features from the different feature groups, and then we can proceed with defining the metadata for the new training data set. So as here, when we create the metadata, we can specify the transformation functions that we want to apply per feature. So here we can see that also we can reuse the same function in different features. And also, as I mentioned at the beginning, here you can specify if you want to compute the statistics. So in this case, we need the descriptive statistics and the distribution of the feature values in order to compare them with the prediction logs that we will be collecting later and detect outliers and drift. So after creating the metadata, we can call save, specifying the query that will be used, and then after that we can already see the values of the training data set. So once we have the training data set generated, we can define an experiment. Like we can see here, we use again XSpace to get the training data set, and then we will just train a simple autoencoder model, simple model that will learn the patterns from the credit card transactions. And when in production, when we in the request will provide the recent activity of a specific credit card, it can detect if it's an anomalous pattern or not, and this is considered if it's fraud or not. So we can train here a simple, a simple model, and then we launch the experiment. I already did that, so we can see here in models, as Jim saw before, that we have already the model created here. And then we can proceed with the next one. I can run these ones because it's faster. So here we will use hops, which is a Python library to interact with the HopSource API to access the serving capabilities, among other things. So we will run these ones for now. Not these ones. So here what we do is to create a serving for this model, so we can specify the path. As you mentioned before, also here in the data sets, we have a folder which is models and all the models that are being generated, all the versions, and inside we can find the model files. So by specifying here where we have the model files, and also we can specify here if we want to deploy a transformer together with the serving with the predictor. So in this case, we want to deploy this transformer script, which is defined here. Basically, we implement a transformer class that has an initialization method where we can connect with the feature store and retrieve the training dataset. This function will run just once when the transformer starts, and then the preprocess function will be executed each time that a request comes in. So we can get this request will just contain the credit card number that the AI-enabled platform wants to check if it's fraud or not. So we can just use the credit card number, which is the key for the feature groups, to retrieve the serving vector. So at this point, the transformation function that we have seen before to normalize the values has been already applied. So, and after that, we can just return the enriched input for the predictor, so for the model to run to make the predictions. So if we go back to this notebook, okay, what else we can see here? We can specify the version of the model. If we want to create an artifact, which is a model package with containing the transformer and the model files and so on. The topic where we want to send the prediction logs, how we want to, which type of data we want to send to the Kafka topic, and the number of instances. So once we run this, notice that here the type of model server has been inferred from the model files. And if we go to the UI, we can see here that the serving has been created and is already running, but we can also do it here, as Jim saw before, and specify the different types of data that we want to send to log into Kafka. And then after that, is running already. So what we do here is to get a sample of credit card numbers from the feature groups, just for the sake of the demo, to make predictions. So before starting with making predictions, we will do another thing, which is start a monitoring job that we have here. I will start it already. And this monitoring job, it's basically an implementation it's a generic job for monitoring and prediction logs that receives configuration either from environment variables or a JSON file from as a parameter when you call it, you execute through the command line. And what is here? Yeah. So an example of this configuration is here, is the one that we were using. We can see that, for example, we can find the schemas of the request and what's the schema also of the instances, which is the the features themselves. What else? We can see which we can specify which statistics we want to compute. Also, how we want to compute outliers, which is based on the descriptive statistics, is if it's more than the maximum and so on. Also, which kind of drift we want to detect, with which kind of algorithms we want to use to detect drift and the thresholds. And also we have here the baseline statistics, which are the statistics computed from using the training dataset. These statistics can be obtained using HSFS, but just for the sake of the demo, I included here in this JSON configuration file. But you can also use HSFS to get the features and use them in the monitoring job. And then here we specify from where we can consume the prediction logs, is this Kafka topics, and where we want to store the statistics, the outliers and drift statistics will go to Parquet files in this directory, and drift and outliers will be sent to these two Kafka topics. So this was running. Okay, but it's not, I forgot to run this. Wait. Okay, so this one is already making predictions, and maybe we have to rerun again the job. No, it's already running. This is not finished yet, but let's see if, okay. So I will continue with the next one. Hopefully there is already data there when I run these cells. So here in this notebook, we will read the Parquet files and the Kafka topics that I mentioned before that we saw in the configuration file to see the statistics that are being computed continuously. So we can execute these ones to check the Parquet files for statistics, distribution correlations and covariance. Let's wait a little bit. This already succeeded, but I'm going to run it again because I started to make predictions a bit later. So as you can see, at the same time that the serving is making predictions, the monitoring job is computing and detecting drift and computing statistics. And we can start taking a look at the files and the Kafka topics. This should be almost done there. And this one. Yeah, we can see that we have already here some statistics. In this case, per feature. Also, we see the window in which these feature values were aggregated to compute the mean, max, mean, and standard deviation. We have also distributions here. Yeah, finally. And the same for correlation and covariance. Let's give it a little bit more time. Yeah, it's still running that one. Yeah, so basically what we can do here is continuously monitoring the prediction logs that are being generated by the model. That are sent to the Kafka topic that we specified before, which is this one here. All right. Yeah, so we start the Kafka consumer to get the outliers that are being detected. That should be faster. Okay, these ones are computed continuously. As soon as one value is available, we check if it's we check if it's outlier or not using the continuous triggers. But these ones are for data that is aggregated in Windows. Since we are using the same credit cards that are already in the feature groups, it might not be, a lot of drift here. So let's rerun it again. And see if we can find some drift. But as you can see, this is continuously being applied on monitor. So if it doesn't appear now, I run it before, so I can show you how it will look like before going back. This is the format that the drift detection will look like. It specifies the window that were used to aggregate the data, which feature showed the drift, which using which algorithm the value of executing this function, and at what time was this drift detected. So okay, this is already looking for it. But again, this is the format that that looks like. So I think this is everything on my side. Yeah. So I will stop sharing the screen here, and maybe Jim, you can show the last slides again.
We can wrap up. I don't think we have any. We need to show any more slides. I mean, I think this is a record-long demo. Emil challenge. Anybody who stayed here, you deserve a prize. So register at hopsworks.ai. You can get an account there and get free access to the cluster. If you link it up to your Amazon or AWS account, you can install the platform on your own hardware, any virtual machine, Ubuntu, Red Hat, CentOS supported, the open source version. And you can reach out to us, if you want to have a demo or you want to find out some more, just reach out to us and we'd love to have a conversation on that. So thanks for attending, and thanks to anybody who stayed the whole arduous 1.5 hours. And thanks Javier and David who's answering questions as well. And thanks Emil above all else for organizing this event. And with that, I think time is out. Thank you very much, and good day to you wherever you are.
Good day.